When a piece of equipment is rated to pull 12 amps at peak performance level with 3-phase power, the 12 amps rating refers to the current flowing through each phase. In a balanced 3-phase system, the current is distributed relatively evenly between the 3 phases. Therefore, each phase is drawing approximately 12 amps. If the equipment is rated for 19 amps using single-phase line-to-line, the 19 amps rating refers to the current flowing between the 2 lines. In a single-phase system, all the current flows through the single-phase circuit. Therefore, for 3-phase power, the equipment is pulling 12 amps per phase, and for single-phase line-to-line power, the equipment is pulling 19 amps between the 2 lines. To calculate amps per phase when it is not directly rated, use the formula amps per phase equals total current divided by number of phases. For example, with 3-phase equipment having a 12 amp total rating, the calculation is amps per phase equals 12 amps divided by 3 phases, which equals 4 amps per phase. For single-phase equipment with a 19 amp total rating, the calculation is amps per phase equals 19 amps divided by 1 phase, which equals 19 amps per phase. Let's delve deeper into 3-phase power systems. 3-phase power is commonly used in industrial and commercial settings due to its efficiency and ability to deliver more power compared to single-phase systems. It consists of 3 alternating current signals that are offset by 120 electrical degrees. This phase difference ensures a more consistent power delivery, reducing voltage fluctuations and improving overall system performance. There are 2 main configurations for connecting 3-phase loads, specifically the Y connection and the delta connection. In a Y-connected system, the 3 phases are connected to a common neutral point, forming a Y shape. The voltage between any 2-phase conductors is known as the line-to-line voltage, while the voltage between a phase conductor and the neutral point is known as the line-to-neutral voltage. The line-to-line voltage is equal to the square root of 3, approximately 1.732 times the line-to-neutral voltage. For example, in a 208/120 volt Y system, the line-to-line voltage is 208 volts and the line-to-neutral voltage is 120 volts. In a delta-connected system, the 3 phases are connected in a closed loop forming a triangle shape. There is no neutral point in a delta system. The line-to-line voltage is equal to the phase voltage. The current in each phase is known as the phase current, while the current flowing through the lines is known as the line current. The line current is equal to the square root of 3, approximately 1.732 times the phase current. Understanding the relationship between voltage, current, and impedance in 3-phase circuits is essential for analyzing and designing power systems. Ohm's law, which states that voltage equals current times impedance, applies to both single-phase and 3-phase circuits. However, in 3-phase circuits, it's important to consider the phase angle between the voltage and current. The power in a 3-phase circuit is given by the formula power E equals the square root of 3, approximately 1.732 times the line-to-line voltage times the line current times the power factor. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates that all the power is being used for useful work, while a power factor less than 1 indicates that some of the power is being wasted. Now let's consider single-phase power systems. Single-phase power is commonly used in residential and light commercial settings. It consists of a single alternating current signal. The voltage in a single-phase system is typically 120 volts or 240 volts. In a single-phase 120-volt system, there is a single hot wire, a neutral wire, and a ground wire. The hot wire carries the current from the power source to the load, while the neutral wire provides a return path for the current. The ground wire is a safety wire that provides a path for fault current to flow back to the power source in the event of a short circuit. In a single-phase 240-volt system, there are 2 hot wires, a neutral wire, and a ground wire. The voltage between the 2 hot wires is 240 volts. This is often used for high-power appliances such as electric stoves, clothes dryers, and air conditioners. The power in a single-phase circuit is given by the formula power equals voltage times current times power factor. As with three-phase circuits, the power factor is a measure of how effectively the electrical power is being used. When working with electrical systems, it is crucial to adhere to safety regulations and guidelines. Always energize circuits before working on them and use appropriate personal protective equipment, including insulated gloves and safety glasses. Consult with a qualified electrician if you are unsure about any aspect of electrical work. Here are some additional points to consider. Firstly, the 12-amp rating on the three-phase equipment likely refers to the line current, not the phase current in a delta-connected system. The phase current would be lower. Secondly, the 19-amp rating on the single-phase equipment assumes a specific voltage, typically 240 volts. If the voltage is different, the current draw will also be different. Thirdly, the power factor of the equipment affects the actual current draw. A low power factor means a higher current draw for the same amount of power. Fourthly, motor starting current can be significantly higher than the running current. The equipment may draw much more than 12 amps or 19 amps during startup. Fifthly, always consult the equipment's nameplate for the most accurate information on voltage, current, and power requirements. Sixthly, use appropriate sized conductors and overcurrent protection devices, such as circuit breakers or fuses, to protect the equipment and wiring from damage due to overloads or short circuits. This selection must adhere to the National Electrical Code, or NEC. Seventhly, ensure that the electrical system is properly grounded to provide a safe path for fault current to flow back to the power source. Eighthly, regularly inspect and maintain electrical equipment to ensure it is in good working order and to prevent potential hazards. Ninthly, use a clamp meter to measure the actual current draw of the equipment under different operating conditions. This can help you verify that the equipment is operating within its rated limits. Tenthly, consider using power quality monitoring equipment to assess the voltage, current, and power factor of the electrical system. This can help you identify and address any power quality issues that may be affecting the equipment's performance. These tools can measure harmonics, voltage sags and swells, and other power quality disturbances. 11thly, when installing or modifying electrical systems, always obtain the necessary permits and comply with all applicable building codes and regulations. 12thly, remember that electrical work can be dangerous. If you are not comfortable working with electricity, hire a qualified electrician to do the work. 13thly, three-phase power is often used to supply motors and other heavy-duty equipment in industrial settings. The three phases provide a more constant and efficient power supply, which helps to reduce vibration and extend the life of the equipment. 14thly, single-phase power is typically used for lighting, appliances, and other small loads in residential and commercial settings. It is a simpler and less expensive system than three-phase power, but it is not as efficient for heavy-duty applications. 15thly, when selecting electrical equipment, it is important to consider the voltage, current, power, and frequency requirements. The equipment must be compatible with the electrical system in which it will be used. 16thly, it is also important to consider the ambient temperature and humidity when selecting electrical equipment. Some equipment may need to be derated if it is operated in high temperature or high humidity environments. 17thly, proper wiring techniques are essential for ensuring the safety and reliability of electrical systems. Use appropriate sized conductors, make secure connections, and protect the wiring from damage. 18thly, regularly inspect the wiring for signs of wear and tear, such as cracked insulation or loose connections. Replace any damaged wiring immediately. 19thly, use surge protectors to protect sensitive electronic equipment from voltage spikes caused by lightning or other power surges. 20thly, consider using uninterruptible power supplies, or UPS systems, to provide backup power in the event of a power outage. This can help to prevent data loss and downtime. 21st, understand the difference between apparent power, real power, and reactive power. Apparent power is the total power flowing in a circuit, while real power is the power that is actually used to do work. Reactive power is the power that is stored and released by inductors and capacitors. 22nd, minimize reactive power by using power factor correction capacitors. This can help to improve the efficiency of the electrical system and reduce energy costs. 23rd, be aware of the potential hazards of arc flash and arc blast. Arc flash is a dangerous electrical explosion that can occur when there is a short circuit in the air. Arc blast is the pressure wave that is created by an arc flash. 24th, wear appropriate personal protective equipment such as arc-rated clothing and face shields when working on or near energized electrical equipment. 25th, follow lockout-tagout procedures to ensure that electrical equipment is de-energized before it is worked on. 26th, never work alone on electrical equipment. Always have someone nearby who can provide assistance in case of an emergency. 27th, know the location of the nearest emergency shut-off switches and fire extinguishers. 28th, if you smell smoke or see sparks, immediately shut off the power and evacuate the area. 29th, call a qualified electrician to inspect and repair any damaged electrical equipment. 30th, remember that electricity is a powerful force that can be dangerous if it is not handled properly. Always exercise caution and follow safety guidelines when working with electricity. 31st, consult with a qualified electrical engineer or electrician for any complex electrical design or installation projects. 32nd, stay up to date on the latest electrical codes and standards. The NEC is updated every 3 years, so it is important to keep your knowledge current. 33rd, attend continuing education courses to improve your electrical skills and knowledge. 34th, consider becoming a certified electrician. Certification demonstrates that you have the knowledge and skills necessary to perform electrical work safely and competently. 35th, support organizations that promote electrical safety and education. This helps to create a safer working environment for everyone. 36th, share your knowledge and experience with others. Mentor young electricians and help them develop their skills and knowledge. 37th, be a role model for electrical safety. Always follow safety guidelines and set a good example for others. 38th, contribute to the development of new electrical technologies and standards. This helps to improve the safety and efficiency of electrical systems. 39th, be proud of your profession. Electricians play a vital role in our society, and their work is essential for keeping our homes and businesses powered. 40th, understand the difference between grounding and bonding. Grounding provides a path for fault current to flow back to the source, while bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. 41st, use appropriate grounding and bonding techniques to minimize the risk of electric shock. 42nd, test the grounding system regularly to ensure that it is functioning properly. 43rd, inspect the grounding electrodes for corrosion or damage. Replace any damaged electrodes immediately. 44th, use ground fault circuit interrupters, or GFCIs, to protect against electric shock in wet or damp locations. 45th, install arc fault circuit interrupters, RFCIs, to protect against fires caused by arc faults. 46th, use tamper-resistant receptacles to prevent children from inserting objects into electrical outlets. 47th, install smoke detectors and carbon monoxide detectors to protect against fire and carbon monoxide poisoning. 48th, develop an emergency plan in case of a fire or other electrical emergency. 49th, practice the emergency plan regularly so that everyone knows what to do. 50th, keep a first aid kit on hand in case of an electrical injury. 51st, know how to perform CPR in case someone is electrocuted. 52nd, call 911 immediately in case of a serious electrical injury.